Hello my friend, you are welcome to my channel, and as you know that this video is a part of our ongoing generative AI course, video course, okay? And as of now, we are learning about Perceptron, and if you have seen my previous lectures, then I have covered a lot of things about Perceptron. I started with the what is the perceptron, what is the mathematical intuition, what is the graphical intuition, right? How the training happens, mathematical, how to understand the training from graphical side, from the mathematical intuition, right? So if you haven't seen the previous video, then I will recommend go and watch the previous recording and where we discuss about perceptron. In this class, what we're going to learn, which is very important concept, is called loss function. Okay, and in perceptron, how the loss function works and what are the loss function, for example, hinge loss. So how the hinge loss work in the perceptron case, what are the different versions of hinge loss, okay, and how the hinge loss work mathematically and graphically. So both I'm going to cover in this video. This video can be a bit longer because I'm covering a lot of maths here. There are a lot of fundamental concept, a lot of maths behind this, okay, and that's what I try my best to explain all the concept. But don't worry, you will learn a lot of things. There's a lot of concept behind that, understanding the loss function. Okay, so let's get us started and let's understand. Let's take a very deep dive about to understand about what is the perceptron loss function, how it works, what is the hinge loss. Everything I'm going to cover in this video in a very detailed manner. Okay, so let's get started and let's understand hinge loss used in perceptron. Let's get started. So let us start. So as we know that in perceptron, what is the purpose of perceptron, by the way? The let's suppose we are working in two-dimensional data. We have two features, right? So the whole purpose of perceptron is what? To find a straight line, to find a best fit straight line so that we can segregate or we can classify two different data points or different classes. This is the whole purpose of perceptron. And for that, how to find the best fit line, for that we perform trainings, okay, which we have already covered. Here I'm showing you couple of cases. Okay, let's understand these cases. Okay, then I will talk about. So let's suppose this is one case. Okay, let me draw this. This is case number 2. This is case number 3. Guys, forgive me if my handwriting is not good, but let us try to understand the concepts. Okay, so let's suppose I have this one data point. I'm just suppose I'm make it green. Okay, these are some one I'm in one cluster. Okay, and there is another cluster. Let me draw over here all the cluster here. So I have a green cluster. I mean all the data points which belongs to one type of group or one type of cluster. Okay, these are greens. Okay, and I have another data points which belong to different group. I'm making it in a green, this color. Okay, I'm just typing it randomly. Okay, just to build the concepts. Okay, let's suppose these are the data points, and here also. Okay, fine. And let's suppose there is one point which is misclassified point. Let's suppose this green point. Okay, there's one point here, this point, let's suppose this point, which should be along with the green cluster, but let's suppose if this point is misclassified and it is very close to red cluster. Okay, same here. And let's suppose I find one straight line, because the whole purpose of training the perceptron is find the best line. Okay, so in order to separate this group and this group, I can draw multiple lines. Okay, there could be multiple possible lines which can be drawn by in a different direction in different tangent. Okay, that multiple lines are possible. That's what I'm trying to say, to separate these two points, these two groups. Okay, so let's suppose here I'm just hypothetically I'm saying let's suppose this one. Let's suppose I found this straight line. Okay, and let's suppose this point is misclassified. That's okay. Let's suppose this is the distance of this point from this line. This line can be a line, it can be plane. If it is in 3 dimensions, it can be hyperplane, anything. Okay, let's suppose here, suppose I find this straight line. Okay, and let's suppose another point is here. This point is here. This is the green point, which is the misclassified point. Okay, And let's suppose I find this point, this straight line, and let's suppose there's a point, okay, the same point, okay. So let's assume that these 3 points, okay, are the same points, okay. uh, I mean the data distribution are same. Let's assume that for time being that data distribution is same in all three cases: case number 1, case number 2, and case number 3. Data distribution is same, okay, and this green points is same in all the cases, okay. Only thing is different in all cases are the straight line, I mean this line, I mean my boundary, okay. So after training, let's suppose after training I found that this is the right boundary in case number 1, case number 2, case number 3, okay. Now if I ask you, I know that this point is getting misclassified. That's okay. We cannot find 100% accuracy. Okay. So I'm assuming that this point is misclassified. This point is falling in the wrong cluster. That's okay after training. Okay. But if I ask you which, here one thing, we know that we can draw multiple lines, okay. We can draw multiple lines. I mean I can find multiple lines which can separate my group, okay. But the question here is which line is the best line, which line is the best line, this is the question, okay. So how to measure that? Though I can draw multiple lines, okay, but how to measure? Question here is, I'm asking this question, though I can draw multiple lines which can separate my groups, but how to calculate? Question is how to measure? Or if I add one terms like quantified, how to quantified, or how to measure the best line? Okay, so do we have some measurement or quantification so that I can find this is the best line? How we can do the comparison? Okay, so you can see that, let us understand. In this case, let's suppose I'm giving suppose this is the distance, okay. For this point I'm calling this error point, okay, because it's an error, okay. So suppose this error point and this boundary, this is the distance, this distance, this distance, okay. So in which case you find that this distance is maximum? Obviously in the third case, okay. So let's suppose with this straight line, with respect to this boundary, this point, can I say that, can I make this statement, this point has more error? Okay, so here I can measure, okay. If I suppose I plot some perpendicular distances, this is my distance d, this is my distance, okay. So from the graph I can figure out that which line has the maximum distance of the point which are misclassified. I mean which line has more error. If the distance is more, okay, suppose in this case in the first case distance is minimum, then distance is larger, then this is the maximum distance, okay. Let's suppose I found 3 lines, okay. So in third case I can say that the error is maximum, because the distance, because this point which is far away from my boundary, it has a maximum distance. I mean this, in this case error is more. Can I say that, can I make the statement, in this case error is more, and in the first case error is less, okay. So this way what is happening here, by measuring the distance, okay, I can make a statement, then I can measure the error by this approach, okay. So which has the less error, which has the minimum error, not less, which has the minimum error, which straight line which gives you the minimum error, I will consider that is a best fit line, best fit line, okay. So this way I can quantify, or I can calculate, or I can measure my error, and this way I can predict, or I can make a statement that in this case this is the straight line which giving the minimum error, and that I will consider the best fit line, okay. So how to do that technically, okay, this what I'm talking about, it's conceptually, but technically in order to find and in order to measure the error, okay, in order to measure the minimum error, in order to in order to measure the minimum error, okay, how to do that technically, how to achieve that. In order to achieve that technically, we use loss function. Okay, so this is the purpose of using loss function. So loss function give me a measurement. I can draw multiple lines, I can draw multiple boundaries. So this is the general concepts. Okay, in in machine learning or in deep learning, right? The whole purpose is what? To find a boundary, and this boundary can be anything. It can be any figure, it can be line, it can be a straight line, it can be any kind of curve figure, it can be plane hyperbola, it can be depending upon the algorithm. I'm just calling it boundary. Okay, so I need to find a boundary, such boundary which will give me the minimum error, there will be error. I'm not saying that your model will be 100% accurate. This is not possible. Hypothetically, it is not possible. 100% accuracy is not possible. It can be, if your model is very good, it can be 90% accuracy, 95% accuracy, but still there are some scope of error. We can accept it. Okay, in machine learning, deep learning, we accept this fact. We are not going to achieve 100% accuracy. But if you are very close to 100%, like 90, 95%, it's okay. There will be some error, okay? But my purpose is that I need to find a boundary after my training such that that boundary can give me minimum error, okay? I have to measure that. In order to measure that, we use loss function, okay? So in order to find a boundary which will give me the less error, minimum error, for that mathematically how to find that, we use a loss function. So this is a complete, according to me, because I come from mathematics background, so I find that it is a pure maths. Okay, this is a pure maths. So I will explain that maths also in this class. Okay, so I hope now, why I was giving these all examples, my whole purpose was to establish this concept, why we need a loss function. I hope you're able to understand this concept. We need a loss function so that I can find a boundary, or I can find some figures, okay, whatever my boundary, okay, so that the whole purpose is what? I want to build a model, such model which has the minimum error. There will be error. I'm not saying it will be 100%, there will be zero error. There will be error. That's okay. We can accept it. But the error should be minimum. So how to find that? How to find that figure? How to find that boundary? For that, we use loss function. I hope now this understanding is clear. Okay. Now, so I hope you got the loss function, right? So in this case, now in this specific case which we are studying right now, perceptron. Okay, I have already created a lot of videos about perceptron. So in this case, in the perceptron case, what is the loss function? Okay, by the way, this loss function is pure math. Even you can calculate. If you're very good understanding about math, you understand graphs, even you can create your own loss function. Okay, this is also possible. You can do research and you can publish your paper. Okay, but here in the perceptron model, already we have defined loss function, which I will talk about in some time, and that's what we're going to study. What is the loss function used in the perceptron? Okay, so in case of perceptron, this is very famous loss function. Usually we use which is called hinge function. Okay, if you guys you have a ML background, then you already know some couple of loss function. For example, in case of regression, right, we use some loss function, right? In case of classification, for example, in case of logistic regression, we has one loss function. In case of support vector machine, we have a loss function, right? So all the statistical algorithm which have some loss function. Okay, accordingly, the same way, even in the perceptron, we have a hinge function which is considered to be loss function. Okay, one thing, my friend, hinge function has a lot of variation. A lot of people don't know that, and they get confused. Okay, His function has a lot of variation. One is called simple hinge function. Okay, simple hinge function. Another is called a squared hinge function. I will talk about that in this class. A squared hinge function. What happened, man? Today handwriting is very bad. Okay, simple hinge function and a square hinge function. I will talk about that. Okay, even in the support vector machine, if you know SVM algorithm, even they use their loss function is also hinge function. Okay, so hinge function has a couple of variation. They, depending upon the algorithm, we make some small adjustment according to the algorithm, and it becomes a different variation. Okay, so I'm not going to cover SVM here. Though I was planning to do a comparison, but maybe I thought it will become a little bit complicated. Okay, so my purpose is not to make it unnecessarily complicated. I want to make it simple. So I will not touch upon SVM, how to use his function in SVM. I will restrict my lecture only for perceptron model. Okay, so in case of perceptron, what is the hinge function? Okay, so if you do a Google, or even you can go to sklearn library. So here I'm just showing, just type Google. Okay, I'm just typing Google perceptron loss function. So you can see that it is Google is giving me this nice article. Okay, so the perceptron algorithm can be understood as minimizing as a specific loss function. So the purpose of loss function is to minimize the error. Okay, particularly in the context of binary classification. Okay, so I'm not going to read that. Okay, so this is a loss function. So this is the formula or mathematical equation of the perceptron loss function, which is nothing but the hinge function. Okay, so this is a function. Okay, so let me explain that. So how we write that? Okay, so let me write that. So the loss function is like this. And guys, don't get scared by this equation. This equation is very simple. I'm going to decode that. Okay, so loss function is this. Loss function is called max 0 minus x into fx. Okay, this is I can write the same equation in different angle, different way, like this also. 0 minus x. Okay, and this fx is nothing but the prediction. Okay, or sorry, it should be y, not x. Yeah, let me remove this. Y into fx actually. Yeah, so y into fx, actually it is called y into fx. Y into fx, or I can write this fx. If you focus on the fx part, fx is called the prediction. Okay, so if you have the understanding of perceptron, in the perceptron, how we calculate the prediction, we do the prediction by this, like minus y. Okay, and here it is weight transpose into x plus b, right? This is my prediction, and same equation is here, right? This, so here this portion y dot this portion wx plus b. If you remember, if you're able to recall the perceptron concept which I have covered, this is nothing but the y predict. The second term is nothing but the y predict. So here I'm doing what? I'm doing the matrix calculation, power propagation. Okay, so this term I'm just multiplying my weight in by x, which is my features, and we adding some bias. Okay, so this is the function. It is called hinge function in case of perceptron. Okay, there are a lot of variation. I'm not covering that, but this is the normal simple hinge function which is used for perceptron model. Okay, now by looking at the formula, it might be little bit confusing for you, I know that. So let me decode this. Okay, so in next 10 minutes or 15 minutes, I'm going to talk about, I'm going to decode this function. Okay, because this is very important to understand. If you understand this loss function mathematically, graphically, then you are done. This is what, okay, let me write in a nice way. So this is what I'm going to discuss in couple of minutes. Okay, so my loss function is this. L is equal to max 0 minus y, okay, and transpose into x plus b. This is my loss function. Okay, now, okay, if you remember, in perceptron model, okay, okay, let us put this way, okay. Here I have one case. Let us okay. I'm going to discuss about what I'm. My purpose here is that I want to decode this formula, mathematical formula, so that I want to make it simple, so that you can understand what is actually a loss function and how it works. Okay. So I have two cases. Case number one. Case number one. Okay. Uh, Max. Okay. Uh, let's suppose if I ask you to do this, what is the max of 0 and minus 2? Tell me, what is the max of between 0 and minus 2? Okay, so obviously the max will be what? 0. So between, suppose this is my line, okay, this is 0, this is minus 1, this is minus 2. Okay, so between minus 2 and 0, which is the max value? Obviously 0 will be the max value, so for this answer will be 0. Okay, if I say what is the max value of 0 and 2, so 0 is here and 2 will be here, 1 and 2. So in this case the max will be 2, right? So here that's what in this function I have two input or two parameter. One is the 0 and second is the this term. Okay, let's suppose this term, if this term, the second term, let's suppose this term become negative. Okay, let's suppose for time being this term become negative, then the loss function become what? Max of 0 and suppose a positive. Okay, uh, yeah, because this is because I have already a negative term. Okay, yeah, so let's suppose this term become positive, because yeah, let's suppose this term becomes positive. Okay, so this whole term is positive, so positive, and because suppose I have positive number and in front of positive, let's suppose 2 is my positive number and in front of positive I put a negative sign. Okay, so this whole thing become negative. This is very simple math, nothing very complicated, right? So if this term become positive, then this whole term become negative. So between 0 and negative, what can be the maximum? It will be 0, right? So this is the case here. I want to explain. I was explaining very simple math. Let me remove this. It's very simple math, by the way. Now I hope you're able to understand. Okay, so now now come back. Okay, so here if I rewrite the same thing, okay, 0 minus y is an actual label, this y. Okay, and this second term, can I write this second term as a y predict? Yes or no? Because this actually wtx plus b, this term is nothing but the y prediction, right? If you know the basic concepts. Okay, so this is my equation, y into y predict. So y is the actual label, okay, and y predict is the predicted level. I'm doing the prediction level, predicted level. Okay, let's suppose this is my data set, which I have been using in the entire class. Okay, suppose this is my data set. Suppose salary is one feature, city is another feature, and purchase happen or not happen is another feature. Okay, and suppose suppose salary is 2 and city is equal to 1, and purchase, suppose I'm saying 1. Okay, let's suppose salary is 3, city is 2, and I'm saying purchase is equal to -1. So 1 shows that purchase happened and somebody bought the product, and -1 show that it's a 2 class one. Okay, so here y, the y is the, I'm calling it y, this part I'm calling it y, and salary is a x1 and x2, and this is my y label. Okay, so here y belongs to, it can be either minus plus 1 or minus 1. Let's suppose I have two groups or I have two class. I'm doing a binary classification problem. So I have two class, 1 and minus 1. Okay. So for 1, I'm saying purchase happened, or minus 1, I'm saying purchase not happened. Okay. So here my y, this y is nothing but this actual label, 1 and minus 1. Okay. And y predict, this is the y predict. Okay. So y predict is what? If you do the forward propagation, let's suppose I'm taking the first data set, I'm taking the first row, 2 into 1, and for 2 into 1 I have some weight and bias, right? So if you know the forward propagation, right, what we do x1 into wt, okay, and weight plus b. Okay, similarly for x2, second x2 wt plus b, this is what we do, right? So we do the forward propagation, right? This all thing I have already covered, right? So if you take this input 2 into 1, and if you do the forward propagation, okay, so the equation of forward propagation is what? The equation of forward propagation is list like this, right? It is x uh, into wt plus b, right? If I take this input and if I apply, if I do this mathematical calculation, right, summation of xt plus b, it will give me what? Y predict. So this y predict is nothing but the same thing, right? This equation, actually this equation nothing but y predict, wtx plus b, what is this? This is y predict. So the same thing I'm writing here, right? So let me remove this. So if you understand this whole concept, right, it's very simple, right? So yeah, so I can write this term wtx into b into y predict. Okay, I hope now you're able to understand. Okay, so what this equation is telling us, so let us understand the meaning of this equation. Okay, so that our understanding will be very simple. Okay, so it tells us that, okay, if y, and here let's assume that I have two class, y belongs to plus 1, purchase happen, and minus 1. Okay, suppose I have two class, so y can be either plus 1, purchase happen, or y can be either minus 1, purchase not happen. I have two class. Okay, so here if y into y predicts, both are positive. Okay, both are positive. Okay, so in this case, what do you mean by that? Case number one, if y and y predict, I mean these two terms, because we have the multiplication of these two terms, right? Y into this term, I'm doing the multiplication. Okay, so if this term is becomes positive, so when this term will become positive, okay, I'm just multiplying two numbers. So when two numbers will be positive, either both, there will be two cases, either both are positive or both are negative. Only these two cases, y into y predict will be positive. I want to make this positive sign. So I want to understand when y into y predict will be positive. There are two cases. Okay, if both are positive, okay, so I have two cases, either both are positive, or both are negative. There are two cases, right? If both are positive, I mean when y, actual y and predicted y, both are positive. Okay, I mean and both, I mean in this case, I mean y is saying purchase, positive is what? Suppose positive is my purchase happened, so I'm saying that both are positive. I mean actually I'm saying that actually purchase happened. Okay, and y predict is also positive. I mean prediction is also saying purchase happened. Okay, so actually purchase happened and my prediction is saying also predict happened, right? So is this in this case, do you find any error? Is it an error case? I'm saying that again, I repeat, I'm saying that actually in my data, okay, in the data set, actually y represent the actual label in my data set, and y prediction representing this equation is representing what? The prediction. Okay, so let's suppose I'm reading the first row. So first row, and this is the case, I have two cases, either both are positive or both are negative. Okay, so suppose both are positive. So when will be both positive? When when y is, suppose I'm saying that y is purchase, I mean actually is purchase case, and y prediction is also saying it is purchase case. So there is no error, right? So this is no error case, I mean it is the right fit, or no misclassification, no error, no error. Okay, suppose both are negative. So when both will be negative, minus into minus, minus into minus will be positive. In this case, in the first case, plus 1 into plus 1 will be positive. I mean my actual is also plus 1, purchase happen, and prediction is also saying purchase happen, right? There's no error, right? In this case, my actual is saying purchase not happen, and prediction is saying purchase not happen. Again, there's no error case. Okay, so if y into y prediction is positive, matlab ki in this case no error, I mean, there's no misclassification. Okay, I hope you got this point. Okay, so what I'm trying to explain here, if y into y prediction, let's assume that y, the label in my data set, is plus 1 minus 1. I'm assuming that. Okay, now if now we have to understand, in case suppose y into y predict, I'm doing the multiplication. Okay, if both are positive, in this case, if both are positive, it means that the point is not misclassified. It's a true point. According to my boundary, there is no misclassification. I mean, there is no error. This point is clear, right? So what I wanted to explain with this whole math, by the way, it's a very simple math, okay? If it's just an elementary 9th, 10th class kind of math. Let me remove this whole thing. Now let's make it clear. Okay, so here I wanted to explain the first case. If y into y dash is positive, then I'm saying that there is no error, no error, no misclassification. Okay, so in that case, this term will be positive, right? And it so, and in front of positive, I'm trying minus. Okay, so in this case, case number one, what is my error? Max 0, and because it's a positive, it will be a negative number, right? Because in front of positive, I'm applying negative, so it will be negative. So what is the max of 0 and some negative number? It will be 0. So here, this equation is telling us, okay, how to, here I just want to show you how to interpret this errors, this loss function, okay. So this loss function is telling us if there is no error, I mean, when y into y predict is positive, the multiplication is positive, I mean, there's no error. Either both is positive or both are negative. There's no error. Okay. So in the first case, if there's no error, your loss will be 0. This is what I wanted to explain. Okay. So here I wanted to explain what, according to my loss function which I have taken, the loss function says that if there is no error, if in my data point, okay, my y actual and y prediction both are same, either both are purchased or both are not purchased, does not matter, but there is no error point in my data set, then my loss is always 0. This is what is the first insight from this equation, from this mathematical equation. You got it, right? Now case number 2, let us understand the case number 2. I tell you this concept, if there is no error, loss is 0. Okay. Now, my function is this, max 0 minus y into y predict. Okay. Now, case number two, let's suppose y into y predict is less than 0. I mean negative. Okay. In case of positive, there is no error, but in case of negative, I mean, I'm just multiplying two numbers and the multiplication is coming a negative number. So in what are can be cases? Just think about mathematically. I'm multiplying two numbers, and by multiplication of two numbers, my number are coming negative. Okay. So there are two cases. So either I plus 1, y can be plus 1 and y predict can be minus 1. Then it can be negative, or vice versa. Either y predict is minus 1, sorry, y actual y is minus 1 and my y predict is plus 1. Then it can be negative. So there are two cases. Okay, in first case, let's think about. I'm saying that y actual is +1. I mean purchase happened. This is the purchase happen case, and prediction is saying purchase not happen. So there's an error. So this point is an error point. I mean misclassified point. Your point is getting misclassified. You're saying that actually purchase happened. Your in data set it is saying that actually purchase happened, but your prediction is predicting that purchase not happen. So it's a problem. Second case, your y actual is saying purchase not happen -1, but actually on the prediction you are saying that purchase happened. Again, it's an error point. It's a misclassification point. Okay, so in this case, if y into y that is negative, matlab ki it's an error case. It's an error. Okay, in the first case, if y into y predict is positive, if the multiplication is positive, there is no error, the loss will be 0 according to my loss function. Okay, but in this case, if y into y predict is negative, I mean there's an error case. Okay, so because it's a negative term, now think about loss function. So loss is saying what? Max of 0 minus y into y predict. Okay, this is what I'm saying. This term is negative, so negative into negative. If I have a negative term -2, and in front of negative, if I put negative, so if you apply basic math, negative into negative positive, it becomes 2. Okay, so this whole term will become what? Positive term. So max of 0, so max of 0 and 2 will be what? 2. So I can say that in this case it will be minus y into y dash. Okay, so the max will be this term. Okay, so let me summarize what we cover. Okay, so my loss function is this. I hope now you're able to understand the concept. So my loss function is this: max of 0 minus y into y predict. Okay, so my understanding, the concept that I want to build here in your mind, concept number 1, if y into y predict is positive, okay, in this case there is no error. Okay, and if there is no error, then conclusion is that loss is equal to 0. If there is no error, there is no loss, right? Case number 2, if y into y predict is negative, okay, then it's an error case. I just established that, right? It's an error case. And if it is an error, okay, then my loss is what? Then my loss is minus y into y predict. I mean minus y into, and for y predict I can write like this: wt into x plus b. Okay, so this is what equation is telling us. Okay, so this equation I can break into two parts. If you really want to understand this equation, you can break in two parts. The first part, when y into y predict are positive, and second case when y into y dash is not negative. Okay, only then you will find two answers, you will find two roots. Okay, so now we have two roots. We can split our function in two parts. When y into y dash is positive, there is no error. We just now learned that there will be no error in that case. Then loss is 0. There is no loss according to my loss function. If the y dash y into y predict is negative, then I'm saying it's an error case. There is a mismatch between the actual label and in my predicted value. There's a mismatch, and in that case I need to find the loss. So the loss will be like this. This is loss function. Okay, so I hope now you're able to understand how to interpret this heavy function or confusing function in two ways. Okay, so if there is no error, we don't have to calculate loss. Okay, and if there's a loss, there's a misclassification, the point is misclassified, then we need to find the loss. Okay, if you're able to remember the update rule, in my previous lecture I had covered perceptron update rule. Okay, So in that case also we discussed that if there is a no error, if there is no error, or the point is not misclassified, in this in the case of no error, there are no change in weight and bias. We had discussed that. Okay, if there are error, then we update our weight and bias. So same concept which we had discussed in the previous lecture using the update rule. The same concept we are establishing using the hinge loss function. So same thing, hinge loss is also saying the same thing. Okay, L is equal to max 0 minus y into wtx plus b. So this equation is also saying the same thing. According to update rule also, and according to the hinge loss also, we are coming to the same point. Okay, so if there is a loss, then this L will be 0, the value of L will be 0. If there is an error, then the value of loss will be L will be 0. If there is no error, then L will be 0. If there is an error, then there will be loss. Okay, so this is what, if I okay, let me talk about graphically what I mean by that. Let's suppose this is my equation. This is my, suppose I have two features x and y. Okay, let's suppose I have two lines. Okay, and let's suppose these are the points which are the actual point. Okay, and I'm taking another point. This is another cluster, red cluster. Okay, so these 2 points, these points and these points are correctly classified. There's no error. Okay, but let's suppose I'm taking one point here. Ideally, this point should belong to red cluster, but this point is misclassified. This is belonging to another cluster. Similarly, if I draw a green line here, okay, so green point here. So actually, this point should come to this cluster, but according to my boundary, according to my model, it is saying that it is belonging to red cluster. Okay, which is the mismatch. Okay, so these 2 points are error. This is the error point, this point is also error. Okay, for these all points which has no error, there is no loss. Okay, if there's no loss, then there will be no rotation. I mean, there's no weight update is required, which we learned in the previous class. So in these cases, if the points are not error, the line will not rotate, there will be no rotation. But the point which has the error point, this point, there will be rotation and there will be a weight update. Okay, so according to hinge loss also, hinge loss is also saying the same thing. It is saying that if there is an error, okay, then we have to find the loss. And what is the loss here? Y minus y predict in case of error. If there is no error, then loss is equal to 0. Okay, so now are you able to connect the similarity between the update rule and between the hinge loss? Basically, both are exactly same, almost same. Okay, so this is what we learned, the first concept here, that according to the hinge loss, if there is no error, like this two cluster, there's no error, it is on the right side, there will be no loss. We don't have to do the update in weight and bias. But if there's a loss, then we have to update our weight and bias, and how to do that I will discover. Okay, this is the formula, this is the intuition of that formula. Okay, one more thing, this is the second part. Okay, second part I want to discuss now. So in the first part, the conclusion, whatever we discuss right now, in the first part, what we discussed, this is the summary of the loss function. Okay, let me summarize. Very simple. If there is an error, there is a misclassification, then according to hinge loss, the loss will be 0. Okay, how we can claim that? We already have seen those examples. Or if there is an error, if y into y predict are negative, there is some error case. I mean, my label and my prediction has a mismatch. In that case, there will be loss, and we have to find the new weight and new bias, and there will be update happen. According to update rule also, we are coming to the same point. So this is the summary of what we discussed as of now in a simple statement. Okay, now let me talk about second point which I want to talk about. Okay, Second point is this one thing. Let's suppose here, before I discuss the second point, I want to teach you first some math here, okay? Then I will come to the point. Okay, let me teach you one basic concept of math. Let's suppose I have a plane. Okay, let's suppose this is a plane. Okay, and the equation of plane is w1 x1 w2 x2 w3 x3 plus b. Let's suppose this is the plane equation. Okay, and let's suppose there's some point here in the space. Let's suppose its point is suppose x1 and x2 and x3. It's a three dimension. Let's suppose these are three points. Okay, and I need to find the perpendicular distance of this point from this plane. I want to find this point, this distance. Okay, so if you do the maths, okay, I'm not going to teach you the maths. Okay, so the distance, I can write the distance like this. How to find? You can do the Google and you can find that. Okay, it's a basic math. So distance of this point from this hyperplane is this. We call it like w1 into x2, w2 x2, w3 x3, okay, plus b by w1 square, w2 square, w3 square. Okay, this is the equation of distance. Okay, perpendicular distance. Okay, that you can do Google. Okay, find the Google that this is how we find the distance. Okay, so here now, if you understand this concept, I will why I'm giving this context in just few minutes. I will explain it. Okay. So my loss function. Now come to the loss function. What the loss function is telling us? Loss function is this: max of 0 minus y wtx plus b. Right. This is what it telling us. Right. So here, this wtx plus b. Can I call it? It's a equation of a plane. Let's suppose it's a two dimension. It can be plane, or let's suppose in more than two dimension, three dimension, four dimension, it can be hyperplane. Okay, so this is nothing but a plane equation. Okay, so can I write this equation? D is equal to wtx plus b. Okay, and you can see that the equation was like this. The distance is what, right? This is the plane equation in the numerator, and in the denominator is a norm. Okay, I call it like mathematically we call it norm, the square of the distance, norm. Okay, so here, so can I write this? Suppose this is my equation. Can I write this equation like this? Can I write wt into x plus b is equal to, I'm just doing a equation. Okay, d into norms of w. Can I write it like this? So this equation, I'm just doing the swiping. This side goes here and this side goes here, so this becomes 1 like this, right? So can I write wx plus b equal to d into distance multiplied by norm? If you if we accept the fact that distance is equal to this, which we discover right now. Okay, so now can I write the same loss function in terms of d? Why I'm doing this whole calculation? I want to write the loss function in terms of distance. Okay, which is quite possible to write it. So loss function, now I can write like this: loss is equal to max 0 minus, see this whole part, actually this whole part can be written as a this whole part. Okay, actually we can also multiply by y. It is called signed distance. Okay, so this whole part I can write into d term. Look at this whole part. Okay, this whole part, you can see that this whole part is nothing but this part, right? This whole part is equal to this part. So can I write this whole part into like this: d norm of w. Okay, so my loss will become this. if I, it is very simple math. It's very simple math, my friend. Okay, so here this one I'm just writing into d term. Okay, I just want to read out the whole term into distance term. That's what my intention is. So I can write, if I make it better, so L is equal to max of 0 minus d multiplied by norms. Can I rewrite this the same thing? Okay, so loss function can be written in this format as well. Okay, so what is the importance of this equation, why I wrote this equation? Okay, so I want to build one concept. That's why I rewriting the whole concept, the whole equation into distant format. Okay, so again see, agar see if, yeah, so you can see that this loss. Okay, we know that in case of error, if there is no error, then loss will be 0. We already studied this concept. Okay, so in case of error, there is no loss, we know that. But let's suppose in case of error, in we have some error. Okay, then this loss, you can see that this loss function can be written as the max will be this, right, d into norms. Okay, so here I want, what I want to establish the concept, the loss is directly proportional to distance. This is what I want to build the intuition. Let me rewrite why I wanted to reach this point. Okay, so my whole purpose why putting this whole context to explain mathematically was to reach this point, what, that the loss function is actually directly proportional to distance. So this is the concept you have to remember. Okay, and how to claim this? By this mathematical formula. It's complete math, I know that. Even my handwriting is not good, but this is the complete math. Okay, this is the distance, and this equation, this portion I can rewrite in terms of distance. Okay, this is distance. Okay, so this loss is nothing but the distance. Okay, if your distance is more, if d is more, okay, if d is more, then loss will be also more. Okay, or vice versa, if distance is less, then loss will be also less. Very simple. Okay, if d is equal to 0, distance is 0, very minimum, or d almost equal to 0, not equal to, if it is 0 means it is just sitting on the plane. Okay, the just hitting the boundary. Okay, let's suppose it's very close, very near to the boundary, this case. Okay, then loss is very 0, loss is almost minimum if it is the points are near the boundary. Okay, so what do you learn from here? So here I explain the first case, right? Go to the first part. Let's suppose this case. Okay, so you can see that in the first case, let's suppose I'm calling it d. This is the distance. Suppose this is my hyperplane. Okay, and this is one error point. Okay, the point which has no error, so there's no loss. We don't have to worry about those points which has classified. उसके लिए कोई पंगा ही नहीं है, right? Those points are correct. Okay, I'm only worried for those points which has errors. For example, this point has an error, and I'm calculating a distance, this distance, this distance, this distance. Okay, so what, according to the loss function, according to the Hinge loss function, what it says, I just now established a concept that L, the loss, is directly proportional to D. This is what I just now established a concept. So what do you mean by that? That if the distance is more, then your loss will be more. If the distance, that this point which are misclassified, if distance is less, then loss will be less. So here you can see that in this case, third case, loss is very maximum. It's a huge loss. But in the first case, it is very near to my boundary. Okay, it is very close to my boundary. Loss is lesser. Okay, so that's what we need to find a state line. We need to find such boundary which has a lesser loss. That's the whole purpose of training, right? So this way you can see that this loss can be measured. Here I'm measuring the loss in terms of distance. So I can say that if I still this concept, so according to this concept, can I say that this line is a fit line because it has a less minimum loss? I can draw multiple lines, okay, just to separate these 2 points. I can draw multiple lines, but which lines is the best line? How I can measure that? So this loss function is doing the same thing, it's doing the measurement. This loss function is doing the right measurement according to distance. If the distance is less, I can consider loss will be less, and that will be the best fit line. Okay, so this is what loss function is telling us. I hope now, as of now, you are with us, with me. Okay, so right now, let me summarize what we have covered. Uh, the concept is very simple, but I wanted to show the maths. Okay, so concept number one is that if no error, if there is no error, okay, this is according to the Hinge laws. Whatever the equation you have seen, Hinge laws. Let me summarize what the Hinge laws talks about. Okay, it tells that if there's no law, if there's no error, loss is zero. Okay, it means that if loss is zero, means I don't need to update my bit and bias. It's okay. Let us keep that. Okay. Second case, if there is an error case, if there is an error, okay, then we have a loss function. Okay, we have a loss. Okay, and loss we know that, but the loss is what, this minus y into y predict. Okay, and third case, I establish that error, if there is error, then loss is directly proportional to d. This is very important concept. Okay, it means that your loss, according to loss, the points which are very far from the boundary, okay, the error point, the point which are misclassified, which are, let's suppose this case, let me draw this, let's suppose draw this. Okay, this is my, suppose this is my line, and let's pretend that these are the misclassified point. Let's suppose these are the error point, this point, this point, these points, these points, these points, these points, these points are the misclassified point, let's suppose. Okay, so the distance, this is the distance from this boundary, this distance, this distance, this distance, this will be the distance, this will be the distance, this is the distance. Okay, so if the, so error, okay, so error is my loss function is directly proportional to the uh, distance. Okay, so for this point, which is the farthest from the line, it because it's d is a more, right? So for this point, the loss will be maximum. For maybe for this point, which is very close to my boundary, less loss is less. Okay, so this is the concept. So the concept says that according to loss, Hinge laws, error loss is the points which are the farthest from the boundary, it is more penalized. Okay, the points, the points which are farthest from the boundary are more penalized. I mean, those points will have more errors penalized. Okay, this is what the loss function is telling us. Just looking at the math, the mathematical equation, what the loss function is telling us. So we build these three concepts. If there's no error, loss is zero. If there is an error, there's a loss, and it depends, the loss depends upon, is it directly proportional to distance. If there's a more distance, then it has more loss, and the loss, if that point is which are very far away from the boundary, it is more penalized. This is what we learn. Okay, and this is what the loss function is telling us. All right. Okay, now moving into the part number three. Okay, so in part number 1 and 2, we just understand what the loss function mathematically tell us, how to interpret the loss function, which is in the mathematical term in our simple language, and we establish these three concepts. We build three intuition or three concepts from the given loss function. All right. Now, here in this part, I just want to extend our concept. Okay, and one thing I want to talk about, this is very important to explain you. Okay, one thing before I talk about the point number 3, I just want you, again, I want to build a context here. Then it will be easy for me to explain the context. Okay. So here I want to show you something, a graph, so that I will talk about a part number 3. Okay. So graph, let us talk about graph. Okay. So I want to show you the graph of two things. Graph of loss function, the mathematical equation. I can draw the graph of that function. This I want to show you. And second, I want to show you graph of derivative. Now, why I'm coming to derivative, I will talk about. I want to show you the graph of derivative of loss function. I want to show you two things. Okay, these two things. This is a context. I'm just building the context right now. Then I will jump to the main point. Okay, but before that, just build this mathematical concepts. Okay, so two things: graph of loss function. So for that, I'm using ChatGPT. Don't worry. I'm using this some ChatGPT just to show you the graph. Okay, so here now let us, whatever concept we have built so far, these 3 points. Okay, these 3 points, I will show you from the graph as well. So for that, I'm using ChatGPT. So here in ChatGPT, I have given just simple prompt: draw the graph of perceptron loss function. Okay, so this is the graph of perceptron loss function. Y is equal to I mean the loss is y into fx, right? This is a loss, right? Y into fx. Okay, and you can see that this is a graph. This is a nice graph of loss function. Whatever you just learned, right? This graph loss function L is equal to max 0 minus y into wtx plus b. Okay, or I can call it like this: max 0 minus y. This part I can call it fx. This is what it is saying, fx. Okay, so this is a loss function. If you draw the graph of this loss function, it will come like this. Come like this. Okay, now let us interpret this equation. Okay, you can see that for this is the this is y into fx, right? This is the y into fx, right? Y into fx. You can see that if y into fx, because this is what I'm trying at, y is equal to fx. You can see that if y into fx is a positive, just focus on this point: 0, 1, 2, 3. So these are the positive point, right? Y into fx, these are the positive point. So for the positive point, the result is what? 0. You can see that for all the positive point, for 1, the height is 0. For 2, height is 0. For 3, height is 0, and so on, 4, 5, 5, whatever. Okay, so for the all the positive, for if y into x is positive, if y into x, now just try to understand, if y into fx is positive, what does mean? I mean, there are two cases. Let's suppose either both are plus 1 into plus 1, or both can be minus 1 into minus 1. Only then this is positive. Okay, in this case, I mean my actual y, and this is the prediction, fx is my prediction. So I mean both are same, my actual y and fx both are same. My actual y, actual label, and prediction both are same. There's no error. Okay, there's no error, right? So there's no error. Then what is the loss? 0. So this point, this horizontal point, is representing when y into fx is positive. This line y into f is positive. If positive, since there's no error, so that is why the height, the result is 0. So what I learned, the concept is 3 concept, right? There's no error, loss is 0. Same thing I am representing by graph. Okay, now if y into fx are negative, so these are the point, negative point: -1, -2, -3, -4, -5. You can see that for the negative point, this height is more. For example, for -3, okay, -3, the height is maximum. For -2, this is the height. For -1, Okay, so if the points are very far away, and in -4, the height it is a linearly proportional, right? So same thing, you can see that if the y into fx is negative, so what I learned here, what the graph is telling us, if y into fx is negative, then there's an error case. Okay, it will be error case, and this error is directly proportional to distance. The more, the farther you go, like if I go very extreme, I go -10, -20, -30, the height will increase. The more you go away, let's suppose I'm going extreme side, -4, -5, -6, the height will be increasing. Okay, so it establishes this concept, right? These concepts that yeah, your loss is proportional to distance. The farther you go, the loss function, the hinge loss function, penalize more you. Okay, that's what I learned here. These three concepts. Okay, these three concepts. Same, it is represented by graph. If you're able to decode or interpret this graph, what this graph is telling us, the hinge function, hinge loss function, it is telling the same thing that we learned right now. Okay, no error. If there is a if y into f is positive, there's no error, and if it is an error, it is directly proportional to distance. Okay, and this is what chat GPT telling us. Okay, y into fx is the margin. If I'm calling this product is a m. Okay, if m is positive, okay, if y into fx is positive, then I'm saying that point is correctly classified. There's no misclassification, and in that case my loss is 0. Okay, if m is negative, then the point is misclassified and there will be error. Okay, and I can say that my loss is proportional to m. The more m, I mean, you will go farther, your loss will be maximum. Okay, and this is what I'm saying. If m is positive, then there's no loss, no penalty, because everything is okay. I don't need to update my weight and bias. Everything is okay. But if m is less than 0, this case, okay, error case, okay, then there's an error, and just focus on this point. The loss increases linearly with the m. The farther on the wrong side, the larger the penalty. Okay, so same concept I established from this. Your loss is directly proportional to distance. The more you go away from your boundary, the more you go extreme, your loss will be more, and you will find more penalty. This is what you learn. These 3 points, same you can learn from this graph. If you able to just understand this graph, what this graph is telling us. I hope you got it right. So this is the graph of loss function. Now, I want to talk about one more thing about derivative. Now, you might be thinking why I need to plot the derivative graph. Okay, what is the purpose behind that? Okay, let me tell you that. The purpose of showing you derivative, okay, to gradient descent, for the gradient descent. Now, I hope this word is not new for you. If you have a ML background, then I hope you know that what is gradient descent. Okay, so let me tell you, if you don't know, gradient descent is a technique. It's called optimization technique. Optimization technique. This is the optimization technique. Okay, to find the minimum loss. I will discuss right now. Okay, so here before that, I talk about. Uh, I want to draw the graph of this function, derivative of this function. Okay, what is derivative, by the way? Okay, let me explain that. If you have a math background, then you understand what is derivative. If you don't know, then let me tell you. I know that these all are very mathematicals. I know that what is derivative. Okay, let's suppose I have one function y is equal to fx. Y is equal to fx. Okay, I want to understand if I change my x. Okay, if I change my x, suppose I change my x, I'm changing x, because y, the output, okay, this y is dependent on x, because we have a relationship. We have relationship between y and x. So according to relationship, if I make some change in x, it will also change y. This is clear? If I'm writing this equation y is equal to fx, it means that there is just some relationship between x and y. There is some relationship. So if I change x, obviously there will be change in y. So how to measure that? How to measure? How to find the change? Okay. So for that we use derivative. So we write like dy by dx is equal to fx by dx. It's a calculus. I'm not going to, I hope you have the basic understanding. Okay. So basically we find the, if I change my x, then what is my update, what the change in y. Okay. And let's suppose this is my graph. Let's suppose this is my loss function. This is my loss function. And the graph is like this. I have just shown you, right? Suppose this is 0. And graph is just, it's a linear like this, falling like this. And here for, suppose this is my x is equal to 0, and this is negative point, -1, -2. And afterwards, after positive, okay, it becomes constant. It's like straight line. Okay, this is height is equal to 0, and this is like this. Okay, now how to find derivative? Okay, so derivative is nothing but tangent. It's again, it's a mathematics. So graphically, the derivative is nothing but the tangent, or it is also called slope, or I also call it tangent. Tangent. Okay. So guys, suppose for this, how to find, how to draw tangent? Okay. Let's suppose, let me give another example. Let's suppose this is, let's suppose this is the graph. Let's suppose this is the graph. This graph. In order to draw a tangent, okay, I just here draw a line like this, like this. Okay, so this is called tangent. Suppose at this point I can draw a tangent, or I can do a slope. At this point I can draw a slope. At this point I can draw a slope. Okay, at every point we can draw a slope. Okay, so this way, so you can see that if my x, if this graph is falling down, if it is falling down, okay, then my tangent will also will be negative. Okay, tangent is nothing but the tan theta. Okay, we draw a line with some angle. Okay, depending upon the height or depending upon the increase of my input, I just want to find the change. So I just draw a tangent. If x will increase, suppose this portion, okay, this portion is increasing very rapidly, so your tangent will also increase, your theta will also be, angle will also increase. So it shows that if my x is increasing, okay, then my slope, I'm calling f, is also changing, is also rapidly changing. If my x is decreasing, then my slope is also decreasing. This is called tangent concept. Okay, let me remove this. I know that this are a little bit mathematics involved here. Okay, fine. Okay, now if I ask you draw a tangent, suppose this is my 0. Okay, draw the tangent after in the positive region, in this region. Okay, so this portion I want to draw a tangent. This is my loss function graph. I want to tangent on this line. Okay, so tangent here will be like this. It will be parallel to, suppose this is my ground, this is my x. So it will be, if I draw a tangent here, slope here, so every point, let's say at this point, so it will be parallel to x. It will be parallel to x, parallel to x, parallel to x. Okay, so it means that here my slope and my tangent is 0. If it is parallel to x, your slope is 0. Okay, it means that if my x is increasing, okay, suppose x is 0 here, x is 1 here, x is 2 here, x is 3 here, x is 4 here, my x is changing, but my slope is not changing. There's no change. M is m is constant. M is not changing. Okay, so here for this, because these are the classified, these are the correct point, these are the correctly classified point for this reason. Okay, there's no these points are on the right side. There's no change, there's no problem with the data point. These are the no error. Okay, so because my derivative is not changing, though x is changing, but my slope is not changing. So in this case, I don't need to update my weight and bias. Again, same concepts. I'm explaining the same concept in different angle. Okay, so for this reason, because my this line is a very constant line. Okay, there's no change happening. All the point for x1 to the height is same. You can see that for even for 1, height is 0. For x is equal to 2, height is 0. For x is equal to 3, height is 0. So there's no change. For given x, my height is not changing. Okay, so that is why slope is 0. So that is why for this point, which are the classified point, correctly classified point, I don't have to update my weight and bias. Okay, now think about this point. These are the error points. Okay, so these are -2, suppose -2, -3, -4, here -4, -5. So these are the reason which are the misclassified points or error point. These are the error points. Okay, so you can see that for the error points. Okay, if you just draw the slope. Okay, suppose here I draw a slope. Suppose I'm taking this point, this point, this point. I'm just randomly taking some point here, this point. Okay, if you ask you draw a slope here, at this point slope will be like this, at this point slope will be like this, at this point slope will be like this, at this point slope will be like this. Okay, so at every point slope m, I'm calling it m, will be -1. M will be -1. So for every point m is equal to -1, m is equal to -1. Slope is always, so you can see that slope here is, slope is equal to -1 for every point, at every point, for every point. Okay, so what do you mean by that? It means that though your points are very far away, okay, I mean this is the case where so like this, though your points are very far away, okay, very far away, but when I'm calculating for all the points, those points are very far away from my boundary, but for all the points the slope or derivative is coming -1 constant. Okay, so how the while calculating the derivative or gradient descent in case of perceptron loss function, it does not matter how far the points are, does not matter, its derivative is always constant, so the change in the weight and bias will be almost constant. It does not matter whether your points are very far away. Okay, it will be a gradual change. This is the concepts. Okay, so if you see the graph, so okay, if I this is my actual graph of perceptron loss function. Okay, next thing I want to draw the graph of derivative of this function. So if you see that, so this is the graph of derivative. Okay, I just put this prompt, draw the graph of derivative of perceptron loss function, and ChatGPT will draw a very nice graph. Okay, so this graph says that, you can see that for positive point, for here for y is equal to fx is positive, so these are the reason which has no error. So for the no error, my slope is 0. Slope is 0, I mean there's no change. It means that if your points are classified, you don't have to update your weight and bias. If you apply the gradient descent, your slope will be 0, there will be no change. Even according to gradient descent, there will be no change in their weight and bias for the classified point. Same concept. Okay, for this point, for negative point, where my y into fx is equal to negative. Okay, so for this area, here I want to draw the tangent. So for all the tangents, it is coming -1. You can see -1. So whether at point -3 you draw a tangent, it will be -1. At point -2, -1. At point -1, -1. You take any point. Okay, I mean between -infinity to 0, you take any point, at all the point your slope or derivative is going to be -1, and it's a constant. It means that it does not matter how far the point is from your boundary or the misclassified point or error point. It does not matter. If you apply the gradient descent, the change will be constant or minus. Okay, so this is a concept. So you can see that for m is negative, Okay, I mean when the y into fx is negative, okay, for the negative point which has the error point, derivative is equal to coming -1. For this point, derivative coming -1. Okay, it means that slope is constant negative for all the point from -infinity to 0 till 0. The point, the slope, the change is negative, which is a constant. Okay, so loss decreases linearly as margin increases towards 0. Got that? Okay, it means that does not matter how far the point is from the boundary, does not matter, or the error point. If you apply gradient descent, if you apply the tangent or slope or derivative, it is coming to constant. So the update happen constantly for all the error points. For m is equal to positive, derivative 0, I mean no penalty. For this case, the slope is 0 because these are the no error point. So for this case, no penalty, no gradient contribution. So all the points which are classified, correctly classified according to gradient descent, there will be no change because the slope is coming 0. Okay, and m is equal to 0 at this point. It is an at this point we cannot find derivative. Okay, so we cannot find derivative at that point. Okay, so what is the interpretation? So for the misclassified point, okay, I mean this reason, for this reason, which are far away and which are the misclassified. So for the misclassified point, always push the weight in the same correction direction. It does not matter how far the point are, it is always update in a constant way, -1, -1. Okay, and for correctly classified point, do not affect the training at all. So it does not update the weight and bias. Okay, so that is why uh, according to this loss function, okay, Hinge loss function, it does not matter. Okay, so here in part 2, okay, so in part 2 I wanted to explain these concepts. The conclusion of part 2 is this. Okay, part 2 says that uh, it does not matter. Okay, if points are, if the error points are far away from boundary, okay, it does not matter. It does not matter for gradient descent, does not matter for gradient descent. Okay, so the change, the conversion, the change will be constant. Change will be constant. So that is why uh, it takes a lot of time to converge. Okay, let's suppose we have, let's suppose I have multiple error points. Let's suppose I have, this is my line, and I have multiple error points, which some points are very close, which are close to the boundary. Some points are very far away, very far away, very far away, very far away. So these are the points which are very far away. Even for these points, okay, if we apply the gradient descent, okay, so what is my gradient descent? This for weight. If you see the loss function, okay, your loss function is this: max 0 minus y into wt x plus b. Okay, so can I see that suppose for a given data point here, y and x are given. I know the value of y, my actual label and input. These two are unknown. These two, x and y, are the known value. These are the known value because I know in my data set I have given, I know the y level and I know the input level. Okay, only thing which is not known is the w and b. These two are unknown. It is known. Okay, so I can say that L is actually function of w and weight. Okay, w and bias. So L loss function is but the function of weight, loss and bias. Okay, so the purpose of loss is what? I want to find such weight and bias where my L is minimum. Find the L so that L become minimum, okay, for given weight and bias. So this is the function. This is what according to my gradient descent. Okay, according to gradient descent, what we'll find? We find such loss, such weight and bias, because loss is a function of weight and bias, so that my L become minimum. my loss become minimum. This is what we call gradient descent. Okay, and according to gradient descent, it does not matter. The concept is that it does not matter how far the points are. Okay, the conversions will be slow. It will be in the constant matter. Okay, it does not mean that if the points are very far away, the rotation will be very drastic. Okay, the rotation will not happen drastic. I mean, for this point, this will be drastically rotate like this. It will not happen. It will be slow. It will be like in the constant way. So that is why sometimes if it is a lot of errors, then your model will take time to converge, because the gradient is not changing very fast. The gradients are changing at very slow pace in loss function, in the Hinge loss function. So that is the intuition of Hinge loss function. Okay, so how to find the gradient? Okay, we have to, for example, this loss function. If I saw the loss function, okay, this is the loss function. Loss function is this, right? Max y minus y into w x plus b. Okay, so here only unknown is my weight and bias. Everything is known. Okay, so I need to find the dl by see here I need to find b w and b. Okay, so that my loss become 0. So I will because I need to find that if I change my w, then how the l will change. If I change my b, then how the change will happen. So I need to find the derivative of l with respect to w. Okay, and I need to find the derivative of l with respect to b. Okay, so these two derivative I need to find out, and then if I find the derivative of this one, then I can update my weight. So the update of weight will happen like this: w is equal to w plus eta. We take some learning rate, okay, which is like 0.01, okay, into dl by dw. So this will give me a new weight. Okay, this is how the weight will update. Okay, and for the bias, it will update like this: b plus n dl by db. This will update like this. Okay, so here what I'm trying to say here, this weight, this dl by w, dl by del w. Okay, for all the points which are very far away from the line. Okay, there the change is almost constant, -1 for all the point. It is -1. It does not matter whether your points are very close to error line or it's very far away. This term is always constant. Okay, so that is why it takes time. If you have a lot of errors, let's suppose in your data points you have a lot of errors and very extreme errors, then your derivative will take time to just converge, and it will take time to find the right weight and bias. Okay, so these are the some concepts, my friend. I know that I took a lot of time. Okay, but yeah, so these are the concepts here. So let me summarize. Okay, if I ask you what is the summary of this in one line, so the loss function is this. Okay, max of 0 minus y into w x plus b. This is loss function. Okay, and there are some cases. Case number 1, if in this case, okay, I'm calling it y predict. This I can also simply say y predict. Okay, if y into y predict is positive, then it's a no error case. Okay, if there's no error, l is 0. No, there's no error, and derivative gradient descent will not play any role here. Gradient descent will not do any contribution here. Okay, because the slope will be always 0. Case number 2, if y into y predict is negative, okay, then there will be error case. It's a error case. Okay, and in the error case, the loss function is written like this: y is equal to minus y into w x plus b. This is my loss function. Okay, and loss function is also directly proportional to d. Okay, I mean, if the points are very far away, your loss will be it will be more penalty. Okay, and third thing, we understand that your derivative, okay, with respect to derivative, that dl by dw is always constant. Okay, always constant, -1. Okay, so it says that it does not matter how many points you have or how many points which are far away from the even though distance is very large. Okay, it does not matter. The conversion will be it give the constant way. Okay, it change the derivative change in the constantly when we apply the derivative or gradient descent optimization technique to find my variant bias. So conversion will be less. Okay, so it does not matter that if my distance very far away, the rotation of the line will be very drastic. It is not like that. Okay, it will be a smooth way. So in the Hinge loss function 1, in this function, it does not matter whether your point is very far away. It's always a smooth conversion, or it's slow conversion, you can say. Okay, and these are some concepts. There's another version or another variation of Hinge function. Okay, it is called a squared Hinge function. I'm not going to cover that. It is called a squared Hinge function. This is your task. You just find out square Hinge function. So in this case, loss is written like this: max 0 minus y into wx plus b. Okay, we do just the square of this term. We just apply a square. Okay, so if you apply the square here, the algorithm just keep change. Okay, so here in the derivative term, okay, if you apply the derivative, it is directly proportional to distance. In this case, in the first case, if you don't apply square in the simple Hinge function, your derivative is almost constant. But if you apply square function, just try that, it will be directly proportional to d. It means that if the points which are very far away from the boundary line, the derivative changes very fast for those points. Okay, so the conversion can be faster. So if you have such points where you're getting slow conversion, or there are a lot of errors, you can apply that. But generally we use Hinge function, which we discussed right now, the first part. Okay, so these are the intuition of Hinge function. I know that it was complete mathematics, but this is how it works behind the scene. Okay, so yeah, I know that there are a lot of things to cover it. Like I can cover one thing. This is your task. Just do some search about uh, how to apply Hinge squared loss in Perceptron, and how the derivative gets changed, and how the conversion happens. Those things you can explore more. Okay, and here I can do one thing which I could not did right now, like finding the derivative. Okay, I can show you like how the weight updates happens with respect to derivative, which you can which if you have the concept of gradient descent, you have ML background, then you can easily find out. Okay, so this is all in this video. I hope you got some idea. I know that in maybe the first time it can be a little confusing if you have no math background or you have no ML background. It can be confusing, but if you repeat this video, I think it will be 100% clear. Okay, so this is all in this video. It was about to cover the Hinge loss function in Perceptron, how it works. I discussed the mathematical part and graphical part, everything. Okay, so this is all. I hope you got some learning in this class, and keep learning. I will come back with the next chapter, and till then, goodbye, take care, keep learning.